Good morning, everyone, and welcome to today's webinar. Before we get started, I'm going to cover a couple of housekeeping items. We'll ask that all attendees remain on mute throughout the presentation. If you have any questions, feel free to use either the Q&A button or the chat button. We will send out a copy of the recording and presentation. That should come out in the next day or two. So look for an email that will come from the IES Zoom user account. And now I'm going to turn it over to today's speaker, Chris McGraw, who is a regional manager with NC State's Industry Expansion Solutions. Chris, I'm going to turn it over to you now.
All right. Thank you, Susan. For those that I haven't met, my name's Chris McGraw. I do work in the Asheville area for NC State as a regional manager. I've worked in manufacturing for nearly 20 years and worked for the university for just over 20 years. We're going to be talking today about additive manufacturing. And this graphic here on the screen talks about Industry 4.0 and all the different parts according to that. You see everything from cybersecurity to Internet of Things. We're going to concentrate on additive manufacturing today. Specifically, we're going to talk more about application, not how to do it. So more toward the end product versus the application. We will talk a little bit just up front so we have something to speak to, but that's going to be our primary function. You will occasionally hear me, I might break down and say 3D printing instead of additive manufacturing. More politically correct term right now is additive manufacturing, but 3D printing probably is just as common a term. So if you hear me say that, just know that they're interchangeable terms. This is the seven basic types of additive manufacturing that we have kind of classifications into. You can see everything there from vapors to binders and different ways to do that. And there's an eighth version, which is kind of a hybrid of these, where they might have the additive manufacturing machine in line or combined with subtractive equipment, think machining centers. So the additive manufacturing would do their part, and then the part would move over to the machining center and be further machined. The main materials that are using additive, you can see there everything from metals, polymers, food, concrete, all these are potential additive manufacturing materials. There's various levels of maturity for each of these as far as how progressive the technology is for each of these. For example, polymers are probably the most advanced of the group because there's been a lot of work done in that area. Metals are still coming. There's some issues around porosity and density and things that's still being applied and still being worked through for more sensitive applications. But generally, all these have different applications. Even food there, you notice at the bottom, we can 3D print food as well. Real basic covering what additive manufacturing is. Basically, somebody comes up with a drawing. See, this looks like I think it looked like a chess piece to me, so that's what I've been calling it. So they have the chess piece looking. We have a drawing. It converts it to a G code, which is what the machine would understand, which can be read by the printer, and then it builds the part up layer by layer. So it would start with the blue section, just a layer, make another layer, just keep building up. Think about that versus additive versus subtractive, which would have started with a bigger block and had to drill holes and all different sort of things to get to the same basic shape. So that's kind of where we are from the technology and how the basic additive manufacturing works. This is a process map for a additive manufacturer powder process map. What I want to show here was that most additive manufacturing, you don't put in the part and get out a completely finished part when you're done. There are some that do that, some applications, but a lot of times we have to do that, what's in the red box there, as post-processing. Once it gets through the machine, it may have to be heat treated, other things. It may be connected to the base that it was made upon. All these kind of things. You may not have the finish that you want. You may have to do some polishing. So there's going to be post-processing. So I don't want the illusion that, that 3D print, additive manufacturing goes and you'll get it's going to be the catch-all for everything. It's going to help where you do and hope it and gets through that process, but it'll get you to a certain level, and then you may have some finishing operations toward the end. I have a kind of a love-hate relationship with this slide because it says pros and cons, and it shows a lot of things that are sometimes always. So we're going to talk about this. I'll try to tell you some of the exceptions to these rules as well. One thing you'll hear me say maybe more than once is complexity is free in additive manufacturing. What we mean by that is that you can make anything as complex as we want up front, and the manufacture is not even any more difficult because it's a complex shape. Whereas with traditional manufacturing, if we have a complex shape, we may have to do a lot of work to get to that. Whereas in additive, it's actually fairly easy to do. It allows probably the most common application is the rapid prototyping that we see. People have done that for years, and that's still probably one of the more common applications. We can reduce lead time, and when you're talking about overall lead time, we're talking about lead time including things like building fixtures for traditional machining or building molds and things like that. And we have very few design constraints within additive manufacturing, whereas with traditional manufacturers, a lot more design constraints. Also, less material waste. So think in terms of environmentally, if I can make a part and don't have to cut anything off of it or have very little material to be removed, then I have less waste, less things going to the landfill or have to be dealt with whatever way. And we can have a digital inventory, meaning there that instead of having actual physical parts, we as a manufacturer can potentially have a digital inventory and just make, manufacture on demand from that digital inventory. Some of the downsides of additive manufacturing, one is it's going to have slower build rates in general. It's you're not going to have fast turnaround. These things take time to build the layers. Initial product cost per part can be more because it takes longer and things along that line. There's still going to be a learning curve. How do we use this process for designers? We have to get technicians up and running on how to work with equipment, those sort of things. Again, as I spoke to earlier, post-processing is required, and it's limited by the size of your machine. And this is one of those that it can be a little bit of a false statement, and it's limited components, but it is limited by the size of the machine. But we have people 3D printing homes now. So that's obviously not limited by size, it's just a different application. So there's some exceptions to these, but that's kind of the general pros and cons of additive manufacturing. Talk a little bit about what makes a good additive manufacturing geometry. Again, it's things that are going to be hard to manufacture using traditional methods, things with passageways, internal lattices, and those sort of things that are more difficult to manufacture. Prototypes where we would have to use expensive molds or custom tools are a good application as well. And geometries that fit within the machine. Again, that we need to consider that as size. And the fourth one there talks about design with topology, optimization, and generative design. If you look at the picture at the bottom, the picture on the right is more traditional manufacturing, where the one on the right would be designed with some design action. We'll talk a little bit about that in a slide further down the road. But you can see just the difference in the complexity and how it would design between the two, from additive to traditional. Things that are not a good fit. Anything that can be made easily on a lathe or mill is not going to be a good application. You see the two examples here. One's basically a piece of pipe that has to be bent, and the other is a bracket that has to be bent a couple times, maybe punched. These are fairly simple and they're not going to be something you're going to look at for additive manufacturing unless you just needed one. Maybe it might make some sense there, but for generally, it's not going to be something that we're going to look at for additive manufacturing. When we use additive manufacturing, we need to make sure it's the right tool for the job. It's not the tool for everything. Example here showing the old style hammers versus the new style hammer. What we don't want to get in the habit of is using additive manufacturing to try to save us. It's because I'm late. I need to use additive to get to that point because I didn't plan ahead where casting might have made sense. So we want to choose the right part. Just don't assume the additive is the perfect fit for all. But we'll talk about applications as we get into it. Additive manufacturing is going to disrupt some industries, particularly molding, injection molding, machining are shown here. It's going to disrupt them in the fact that we can change the way things are going to be made. They're going to change the way we look at things from that. It's going to add to it by adding innovation to these processes, reducing time and efficiencies. Some of the industries that have been disruptive, think about if anybody's had kids or had them themselves, the Invisalign system for the braces. These are 100% additive manufacturing processes. So they can be made, they can do that, and they work through that process. Another one is hearing aids. You can see there from the term, it says hearing aids went from zero additive manufacturing to 90% in 500 days. So basically a year and a half, that industry changed completely from to more traditional to additive manufacturing as the primary way to be done. The bottom of there shows custom jewelry market, where people are making sample jewelry, stuff they like to make, or it might be trying to make a traditional something more time say I want something from the 1920s style, or maybe you're making a movie or photography and you need a specific type of jewel that you want to recreate. They use this to make the wax models that they can pour and make jewelry out of. So that market uses additive manufacturing pretty heavily as well. So those are pretty innovative ways, things that we can use for our additive manufacturing processes. Okay, we're going to talk more now about the specifics of applications and how people are using it now, and hopefully how we'll look to use it in the future. I want to kind of highlight the 6 things across the top, so we're all understanding where we are. This is the basic product life cycle curve that we use when we describe products. First one, ideation. Somebody comes up with an idea. This is something we might want to create. It has some potential applications. Let's look at it. Prototyping. How are we going to check it? Is that something really is good? We're going to make something. However we're going to do that. We'll talk about different ways. Then we're going to start getting to where we start making the things. We feel there's a market. The prototype's working. We're going to ramp up, and we're going to try to get to that, where we're making that on a regular basis or in the whatever's needed for the market. Then maturity. Maturity is when it's there. The market's there. We're making it in our manufacturing facilities. Things are going well. But then ultimately, those products will be replaced. They're going to go in decline. We'll get something newer, better, faster is coming along, and we're going to be in that decline part of that curve, if you will. Then the last part is end of life. That's back, things think about spare parts down the future for older equipment, things like that. So how are we going to handle that end of life cycle as far as that? And we'll talk about how that fits in with additive manufacturing as well. So the first one there we're talking about is first the early adopters for additive manufacturing. And primarily it was in those first 2 boxes, the ideation and the prototyping. People were doing things around concept models for our ideas, how we do that. This might work. Sometimes it's functional, sometimes just for a fit, make sure it fits where it's proper. And then we started to be able to do functional prototypes, things that actually can work for what we're doing. So it becomes something we can actually try and use and do different ways. Yeah. Okay. I'm not advancing for some reason. Excuse me for one sec. I'm not sure what's going on. Up there it went. Hold on. Went too far. Okay. I'm working again. Thanks. Sorry about that. You want to talk about panic from presenter? There you go. Additive manufacturing stage 2, looking at the next level of things that we can possibly do. Here we talk about rapid customer testing. I can now do a series of tests. I can make something. The customer tells me, yeah, that's great. No, it's not. It worked for me, but it didn't work for my person in the office because they're left-handed and it didn't work for them. Whatever it is, we can start looking at making a lot of different iterations and going back and testing with our customers. And we can start making short-run tooling. And by short-run tooling, got a good example here, what we're going to talk about. If you look at the picture on the left, if we do a 3D model of this fan propeller blade here, what we can do with additive manufacturing is actually build a mold. You see where it goes to modeling, and then it goes to the gray picture there where it's actually showing, it's actually here printed the mold. And then we pour the castings down at the bottom left. Now we have a part, we inspect it, and it's a finished part. So now we have the opportunity to test something fairly quickly. If you look at the box in the bottom there, it talks about traditionally that would have took me 6 months from a lead time to get a mold made and had to spend about 70 grand for the tooling. And now it tells me about $500 per casting. So I'm invested just to make the first part, $70,000 plus the $500 for the casting. Whereas with the short run tooling from the additive manufacturer, it took me 6 weeks. There was no tooling investment other than my print time, but it cost me $6,500 to make that one part. But it's still, look at $6,500 worth of $70,500. And now I've got a part I can use and I can test and make that. So for short run, it's going to be a great application, get up running and do some testing and whatever I need to do from that perspective. The next is it can enhance our production in the third stage. We can look at production jigs and fixtures, and I'll show you some pictures of some examples of some of this. We can also use it for bridge production. Think about as I'm ramping up my production, maybe I use my additive manufacturing capability till I get to a certain volume level, or as I'm waiting on tooling to be made. I can get parts out in the field while I'm waiting on my tooling or while I'm getting that. If I use it as bridge production before I decide to move to that, what if the product doesn't take off? Then I've just invested a bit instead of setting up a product line to be able to do that. Also in the maturity stage, there's production tooling. Again, I'll show you some samples of this, but think about things along guides and tech, quality checks and things like that, or tooling to hold things. We have a lot of opportunities around that. And then end of life, we can do spare parts fulfillment. I can print off 1 or 2 spare parts using my additive manufacturing equipment where I don't have to stock up a whole bunch of different spare parts for somebody that might potentially need it. But here I can do it on demand kind of application. So you can see here an example of production tooling. You can see that people are printing different things for holding devices, different things. Potentially, you could come up with a new product that you're going to run tomorrow, overnight, print up the production tools, the fixtures, jigs, and next morning come to work, and it would be sitting there for me to be able to run my next job. So there's a lot of applications around that as well. And we see this out in the field today. Jigs and fixtures, lots of opportunities here. You can see drilling jigs, assembly aids, lots of different opportunities. It can make things, they're complex, simpler, where to put bolts, where to put drills, different things, and look at better efficiency. We can really do quick changeover type applications, use it for quality guides and quality checks as well. This is an example from Porsche, whereas they are now 3D printing their spare parts for their older models. So think about if you just needed a knob for a doorknob when they still used to have crank handles. I just need that knob that's in there, it's broken. They can print 1 or 2. Whereas in the past, they might have had to make hundreds to be able to produce that, but now they can use that if they have the capability to produce them in small quantities. For our 4th stage, we're talking about additive manufacturing enabled products. Before, we pretty much been talking about 1-for-1, going from a traditional product to a additive manufacturing product with the same basic shape and design for the most part to do that. But now with our capabilities, we have ways to design for products using additive manufacturing. So think about that up front versus as an afterthought. We want to think about it up front. So we're going to look at design and then how do we get up to that volume production where we can actually be producing with additive manufacturing. For this, we're going to talk about generative design. The way design can be done around additive manufacturing now is basically, you look at the top box on the right where it says human defines. A person is going to decide, whoever the designer is, where the critical elements in that part are. It's got to be this size, basic length, width, and height. Where do I need holes? Where do I need through holes? Where do I need drilled holes? And give it that basic design. And then the computer is going to use its algorithms and build the part. You see AI generates there. So it goes from where the human says, this is what I need, and the machine says, this is what I can give you based on those needs. You take a look at it, you approve it as a designer, and then the equipment's actually can build the equipment. But you can see just looking at this, that the complexity of that would have been very difficult to design by just normal design methods. So, but we can use the machine's capability to be able to give us this complex design using less weight, less material in places, and save us in a lot of different ways. A big way this is being used now is in the injection molding world, in that we can cool our inserts, our parts quickly and get cooling where it is. One of the things that causes most quality issues in plastics is things along warpage, shrinkage, and things, because things don't cool at the same rate. If I'm trying to make a part that has a thin flange or something on it, if it cools too quickly, it may bend or warp. Whereas with this, we can get cooling to where we need it to be in the right term. If you just look at the drawing there, the picture, if you just follow the purplish color tube, that's getting coolant to the proper area where it needs. We could not ever make this with traditional manufacturing, but with additive, I can make all sort of channels and ways to get things into where they need to be internally I could have never done in the past. So that helps me with my dimensions. I have all sort of flexibility, a way to make things. It makes my designer's jobs easier because he can make what he or she needs to make. And you see at the statement at the bottom that this cooling can reduce their cycle time by as much as 50% by cooling the part and keeping it the way they need to be able to do. Okay. This is an actual example from Airbus. And if those that are familiar with the aerospace industry know, they kill for weight reduction. If I can take weight out of an airplane and start magnifying that by take a pound out here, and then you have 100 of those in one airplane, then 1,000 airplanes in the market, it starts adding up a lot how much weight I can save, which turns around to saving fuel, which is big dollar savings. This particular example is a cabin bracket, and you can see the traditional one on the top, where it's fairly solid. It was done from a traditional machining method. And then the one on the bottom was done with 3D printing. So you can see it took a lot of the weight out. It took about 30% of the weight out, according to what was reported by Airbus. And it saved them 75% cost and the time savings. They said now that they used to allow 6 months for component design. Now they use 1 month for component design for things like that. So imagine the cost savings, the engineering time, the lack of, they don't have to do tooling and things. So a huge advantage for those folks. We can also use our metal additive manufacturing as a foundry internally. If you look at the top where it talks about conventional foundry, we would go to a foundry, say, this is what we need. This is the type of part we need produced. And they would do it for us. They would do the feedstock, make it up, forge it. And then we would get it there in the middle where it says material certification. And we would turn around and use our traditional machine shop to get it to the right size, ground, get the flatness, holes, drill, whatever it is that we need, and have our traditional part there. Well, internally, if we have a metal additive manufacturing, we can do that ourselves. We can do that same feedstock. We can heat it. We can get it to the forge we need, thermal process it, and then it turns into material certification. It follows exactly the same process as a conventional forge, but now we have internal controls, and we can make different shapes. Say if the first one didn't work, we've got options to do different things. So every metal additive machine is potentially a foundry for us. This one is very fascinating to me, is that we can combine parts. A lot of times designers have had to design parts based on manufacturing capabilities. I can't make that, so I have to make 2 or 3 parts to get the channels that I need, or the throughput, the hole I need there, different sort of things like that. So by combining parts, though, we have a lot of advantages. We can reduce our supply chain. If you look at the example they show here, there were 8 parts, and that's not including the little gaskets and other screws and things assembled. It's just 8 main parts. And it would take them 1 week to make these, 8 parts versus 1, And then we reduced the part by making 1 single part with a 35% weight reduction. Not only that, it improves our performance. If anytime I have a potential with gaskets and screws, I have a possibility for things to fail or even be left out inadvertently. Say if I left out a gasket, then I'm going to get leakage and things. Where I can make a combined part, I don't have those issues. So also manufacturing diversification is that I can manufacture it in multiple locations easier now if I only have a simple part to manufacture. I don't have to little part here and a part there. So I can do different things around that as well. This is an example Another aerospace example. And this is they call it an advanced turboprop from GE. This is pretty amazing. They took 855 parts and combined them into 12. So you think about the magnitude of change there for your supply chain. We'll have to figure out how to make 12 things versus manufacturing 855 different parts. They took out about 5% of the weight. Again, remember, aerospace, weight's king, so we can get it out. That's great. Lowered emissions by 20%. So that's, a big deal for them as well. So increase our power and fuel, a lot of advantage to that. So obviously they're heavily looking at any way to do that, to reduce that number of parts by combining these things through additive manufacturing. Up to this point, mostly we've been talking about existing ways and things a lot that are going on now. We're going to talk a little bit about the digital part, the future for additive manufacturing. With our parts now being a digital file versus a hard part, we can use a digital file in a lot of different ways. One is that talks about there about continuous customer engagement. I can always be working with my customer to improve my product. I can, if somebody comes to me and says, this worked great for me, but my 12-year-old son hands weren't big enough to do it. Well, we can redesign a little bit for him. Or somebody has limited mobility, I can design it around them. So we can constantly have that continuous customer engagement by sharing information back and forth. Same with design evolution. We can change things as we go through and look at ways to do that. I can share a file and you can make it your own and change things to be able to do that to help you. We've alluded to this a little bit already, but on-demand production. We can put production wherever you want it. If you had an additive manufacturing equipment at your home, I can send you the file and you can make it yourself, or we can make it wherever it needs. So we can make what's needed when it's needed. We don't have a lot. It's going to help with obsolescence, supply chain issues, potential things around that. Next one, there's distributed capacity. Imagine if I'm a manufacturer now and I have plants in, say, Asia, Europe, and America. I may make one part one place and one another and another. But with this technical advantage of having everything digital, I could actually distribute that capacity across the 3 continents and not really have a huge increase in way to do things that decreases shipping costs. I have direct relations with my customers closer to where I am. So that distributed capacity could be big. Think about the next level. What if Amazon took their top 20 selling items that they could print and they set print stations up at their various locations? Now they could print as needed. Some of their top sellers, print it today, ship it tomorrow, and be to us the next day. So we can distribute that capacity in a lot of different ways. The next one there is interesting from customization and personalization. We can make things specifically for anybody. I mentioned before about the jewelry. People are making things now for action figures. You can make an action figure with your face on it. All these different personalization and customization things, but we can work around that. I have a client that's working on a project with us for additive manufacturing around, they work with police dogs. And they have a device that when they have a dog on the leash, but when it needs to run, they can release it and the dog can go, but they can build the fixtures and things, the harnesses and the things around with our digital additive manufacturing processes and customize it to have that dog the right size for that dog. Put the dog's name and contact information, where to get lost and how to get back to where he needs to be. So there's a lot of personalization things we can do. But we can send you the file. You can do it wherever you want. If one example, think about if you wanted to put your name on your mailbox. You just moved in a new home. You could get a digital file, print your name, put the label on the and have your name on your mailbox. By just personalizing it through those kind of things. So there's a lot of different potential applications moving forward from a digital file standpoint. It opens up a lot of new worlds and things I'm sure we haven't even thought of yet are coming in the future. We at IAS have some additive manufacturing resources, and when you get this file, you'll be able to look at that. There is an online class that's going to be more about the 7 processes that you saw at, I think, the second or third slide. And it'll give you more definition about what those are, how they work, some specific examples. So if you're interested in learning more about that part of it, they can definitely do that. And we have some resources internally to do project, and you can look at the resources here. As we get into that, well, you might have applications and we can come online and talk to you. We can do some similar type small presentations like this one, or if you want us to do an assessment of some things that you have, if it makes sense for additive manufacturing, we're glad to work through that. You just see on that page how to be able to make that connection with us. We'll be glad to help you however we possibly can. And have any questions? I don't know, Susan, if there's any questions or anything I need to answer further.
If you have any questions, feel free to put them in the chat or the Q&A box. We'll give folks a minute or two for that. Chris, thank you so much for your presentation today.
Sure.